Hello everyone and welcome to this review of chapters 9, 10 and 11. Chapter 9 is Capacitors and the Capacitance, and chapter 10 is Inductors and Inductance, and finally putting these two devices together, how tuned circuits work. So firstly, what's the phenomenon of capacitance? Well, it's the ability of a body to hold an electrical charge. Capacitance is a measure of the amount of electrical charge that can be stored, for a given electrical voltage or potential. So basically the most common form of charge store device would be just really two plates. So you just get two plates, you can put a voltage across both these plates, and charge will move from one plate to the other. Basically you just take two chunks of conductor, separated by an insulator, apply a voltage across them, and then one side will become positively charged, the other side will become negatively charged. The capacitance of a capacitor depends on the geometry, and also the material in between the two pieces of metal. This is a very common question on the exam, in that what will physically affect the capacitance of a capacitor? Well, the surface area of the plate, so if you get two metal plates, if they have a large surface area, you end up with a large capacitance. The distance between the plates, if the plates are closer together, the capacitance increases. And the dielectric constant, well, that's basically the material in between the two plates, so it could be air, or it could be another kind of material that can store charge. In parallel, the capacitance increases as you add more and more capacitors in parallel. And a way of thinking about this is, well, that the plate size will increase. If you have two plates rather than one, you'd increase the capacitance. So if you have capacitors in parallel, that the value of the total capacitance just increases and increases and increases. Now, because the voltage is being shared in series, the capacitance actually becomes less. And you've got the rule 1 over Ct is 1 over C1 plus 1 over C2 plus 1 over C3. Why are capacitors useful to amateur radio operators? Well, they will allow alternating current to pass through them, but they'll actually block direct current. And basically, the higher the frequency, the more current they allow through. So there's something called reactance, and reactance basically is like resistance, but resistance that varies with frequency. With a capacitor, as you increase the frequency, the capacitive reactance actually decreases. So it becomes easier and easier and easier for high frequencies to pass through capacitors, whereas low frequencies can't pass through them as easily. Something that's important just to note is the relationship between the phase and current of capacitors, and there's something called civil, C-I-V-I-L, and it will help you remember which way round this relationship goes. So in capacitors, the current always leads the voltage by 90 degrees. So the voltage across the capacitor lags the current by what we call 90 degrees, whereas 360 degrees would be a complete oscillation of a wave. The current actually is ahead by 90 degrees. And we'll find when we look at inductors, the opposite happens. When we combine the two devices, this effect actually cancels. So next up we had a look at inductance and the inductor. So what is an inductor? Well, unlike a capacitor, which is two plates, an inductor basically is a coil of wire. And when a current increases or decreases through a coil of wire, it actually creates a voltage called a back EMF in the coil. Because of the way the magnetic field is surrounding the wire, as the voltage increases, as the current increases, that magnetic field increases, and as that magnetic field increases, it creates a voltage in the opposite direction, effectively acting like a brake. So the higher and higher in frequency, okay, the greater this braking effect. So in fact, an inductor is doing the complete opposite of a capacitor, in that an inductor, as the frequency increases, it will actually block more and more and more signal from passing through. Direct current, which is current that only flows in one direction, basically never changes, okay, except for when the circuit is turned on, so it's not really affected by inductance. Now, inductance is measured in henries, and if you think about it, if you have a series combination, so one coil leading into another, okay, the total inductance just increases. And if you think about why would that happen, well, effectively you're making the coil longer and longer and longer. The parallel combination, well, now you're giving the electricity two different paths to flow through. Okay, so in fact, similar like with resistors, the total inductance is 1 over L total is equal to 1 over L1 plus 1 over L2 plus 1 over L3. So, completely opposite to capacitors, inductive reactance actually increases as frequency increases, so it becomes harder and harder and harder, okay, for electricity to pass through an inductor as the frequency gets higher and higher and higher. Now the phase relationship is the opposite of capacitors when compared with inductors. The voltage across the inductor actually leads by 90 degrees. Now if we add these two pieces of equipment together, we'll actually see we're going to start to create something called a tuned circuit. So just to kind of recap what we've already looked at, in that capacitors, well, they let AC through but block DC. Inductors let DC through but block AC. So if you combine them both together, they would block everything, right? Well, not quite. And it all comes down to this phase relationship. So it's all about civil. The phase relationship of both capacitors and inductors can actually cancel each other out. And at specific frequencies, the total reactance becomes zero. Now, this actually includes complex numbers and imaginary numbers. For the full explanation that's beyond the scope of this course, you just need to understand that at certain frequencies, if you combine the two devices together, effectively you can get the resistance to the flow of a signal to become zero. So on the right here, I've got an example of a tuned circuit. Well, I have an inductor on the left-hand side and a capacitor on the right-hand side. And what's happening is there's energy going from one to the other, much in a similar way that a pendulum would or swings, and that it goes from gravitational potential energy to kinetic energy, or the energy of motion, and back again. Now this is what we call a tanked circuit, or resonant, or LC circuit. When the capacitive and inductive reactance are equal, and you can show that there's a resonant frequency, okay, and that frequency is equal to 1 over 2 pi rho L C. And this frequency in a tuned circuit will either, depending on the configuration of the tuned circuit, be the only thing allowed to be passed through, or the only thing that's blocked. So on the right here, we've got the two different combinations of capacitor and inductor in parallel or in series. So in parallel, DC and AC will pass through except around a resonant frequency, effectively acting like a trap. In series though, both DC and AC are blocked except around a specific resonant frequency. Now, something that we need to go over is something called Q factor and bandwidth. So the Q factor of our tuned circuit basically is to do with the shape of our tuned circuits, what the tuned circuit will allow to pass through this filter, in that you can have a very wide filter which would have a low Q and let a lot of different frequencies go through, having a high bandwidth, or a very, very narrow filtering, so it would only let a few frequencies go through but have a very narrow bandwidth and therefore having a high Q factor. And the equation to work out Q factor, which actually has no units, is the center frequency divided by the upper and lower frequencies, where the upper and lower frequencies actually are at a strength of about 50% of the center frequency. Additionally, there's also another way of calculating the Q factor. And either you can use, because they're the same value, the inductive or capacitive reactance divided by the resistance of the circuit itself. However, this rarely seems to come up in the exam. In fact, I've never really seen it come up in the exam. Okay, I hope that's been a handy little recap. Looking forward to seeing you guys on Saturday.